Hello everyone, my name is Bernardo Patella. I'm a chemical engineer and a postdoc researcher at the University of Palermo. I'm glad to show you part of our research that concerns the development of a nanostructured copper-based electrode to detect nitrate ions in water samples. I thank all the FLEPS 2020 organizers for giving me this opportunity. So now I will start to share the presentation. So first of all, we should introduce nitrates. Nitrate ions are nitrogen-based compound and nowadays represents a significant pollutant for both internal and marine waters. They can derive from both natural and anthropogenic sources. Among the natural one, we find the biological process of mineralization, atmospheric nitrogen fixation, like sediments, igneous rocks, among others. By the way, natural sources don't bring to a real pollution due to the small release of nitrate. Over time, human activities have created imbalances, continuously increasing the concentration of nitrates in soil and groundwater due to many activities such as losses from landfills, geotechnical wastewater, nitrogen-based fertilizers, and food preservatives. These imbalances have created a great problem for humans, for both environment and for healthcare. Indeed, the high concentration of nitrates in water and or in soils leads to soil acidification, to a reduction of biodiversity, acid rain, and eutrophication. The last one is of high impact for aquatic species because it reduces the dissolved oxygen in water. For human health, a small amount of nitrate ions is of wish, but when its concentration is too high, it starts to be converted into more dangerous chemicals such as ammonia, nitrite, and nitric oxide. Furthermore, nitrate ions can oxidize hemoglobin to methemoglobin, reducing the oxygen transport capability. This is a well-known disease called as blue baby disease. Considering all these issues, many European agencies fixed the maximum allowed concentration of nitrate in drinking water to 50 ppm. Nowadays, nitrate ions can be detected by different techniques such as spectroscopy, fluorimetry, electrophoresis, and chromatography. These techniques allow to detect nitrate in the ppb range, so with really low limit of detection, in a sensitive and selective way. By the way, these are just lab-based technique that requires expensive and hard-to-use machines and cannot perform any kind of real-time or in-situ analysis. Electrochemical techniques are perfect candidates to overcome this issue, especially if coupled with nanoscience. Indeed, electrochemistry guarantees a low power consumption, small and easy to use instrumentation, while the high surface area of nanostructured electrodes can help to obtain sensors with high sensitivity, selectivity, and low limit of detection. In this work, we have developed a nanostructured copper electrode made of vertically standing nanowires obtained by galvanic deposition. A polycarbonate membrane has been used as template with nanopores of about 6 micrometer long and 0.2 micrometer in diameters. In the same image, we can see the top view and the cross-section of the template. In order to make the membrane conductive, it was spattered with a thin layer of gold, and subsequent, a copper current collector was deposited by electrodeposition on top of the gold film. The current collector was then coupled with an aluminum tube and immersed into a solution made of copper cations. In this way, the aluminum dissolution produced electrons that reduce the copper cations to metallic copper directly into the membrane's pore. Finally, the membrane has been etched by pure dichloromethane, and an electrode made of vertically standing nanowires has been obtained, and the nanowires are perfectly anchored to the copper current collector. The electrode synthesis was optimized in terms of solution pH, solution concentration, and deposition time. Particularly, increasing the deposition time, the copper nanowire's length increases, as well as the nanowire's density. Indeed, the polycarbonate membrane consists of interconnected pores, and thus a longer deposition leads to longer nanowires, but also to a more compact configuration. The electrodes were characterized by ADS and XRD, showing the presence of only polycrystalline copper and gold. These results in terms of XRD and NDS has been obtained for all the electrodes independently from the deposition time or copper concentration of the solution pH. In order to use the as prepared electrode as an electrochemical sensor of nitrate, linear sweep voltammetry was selected as technique using a platinum mesh as counter electrode and a silver chloride as reference electrode. The sensing platform was optimized in terms of deposition time, solution pH, and supporting electrolyte. To better understand the detection mechanism, a cyclic voltammetry was carried out in the potential range from minus 1.4 volt to minus 0.1 volt in a solution made of 1 millimolar sodium nitrate. Two distinct peaks were found at potential of about minus 1 volt and minus 0.4 volt. These two peaks correspond to the oxidation of nitrate to ammonia and nitrite, respectively. Considering the higher intensity of the peak located at minus 0.4 volt, it has been selected to calibrate the sensor. This slide shows the influence of the surface area. A thin film of copper produces a bed-shaped and low-intense peak, while a nanowires electrode obtained after 30 minutes of deposition shows a much more intense peak. Using a 60 minutes deposited electrode, the signal enhancement is much more pronounced, while interestingly, the peak intensity drops using a 120 minutes deposited electrode. This is probably due to the membrane interconnections. Indeed, as I said before, increasing the deposition times, the nanowires became longer but even more compact, and thus the wettability of the electrode decreases. In order to have a compromise between electrode wettability and surface area, the deposition time was set to 60 minutes. Finally, the effect of testing pH was studied by measuring the peak intensity of 1 millimolar nitrate at different pH. The results show a big effect of this parameter. Indeed, using pH higher than 3, the electrode start to oxidize to copper oxide, so reducing the signal intensity. While using more acidic pH, the peak intensity decreased due to the hydrogen evolution reaction. The best result was found using a pH of 2.5. Using all the optimized conditions, the electrode was put in contact with different amount of nitrate ions, and the signal intensity increases from 10 micromolar to 1.5 millimolar. Particularly, two linear ranges were found as shown, and the limit of detection of 9.1 micromolar with a standard deviation of 5% was found. This is an important result because this limit of detection is almost 1,000 times lower than the limit set by the Environmental Protection Agency. Before to test the sensor with real samples, selectivity tests were carried out. Particularly, the interference from carbonate, zinc, aluminium, heavy metals, magnesium, potassium, sodium, and sulfate were studied. All these chemicals don't produce any particular interference as shown in these figures. Indeed, the peak intensity of 50 ppm of nitrate increases or decreases less than 7% when 500 ppm of all this interference are put together into the solution. So there is almost a negligible effect of these chemicals. Unfortunately, the presence of chloride produces an higher interference even at quite low concentration. 10 ppm of chloride indeed produce a signal decrease of about 10%. This result makes the analysis of many real water samples much harder. Drinking water have a chloride concentration of about 5 ppm, and so its analysis can be still carried out, while natural water samples have a much higher content of chloride, even higher than 500 ppm. For these samples, a pretreatment is mandatory. Here we show a possibility to add silver sulfate to the solution. In this way, silver reacts with chloride, producing silver chloride. This is an almost insoluble compound that's so precipitate. This precipitate has been collected, and the XRD shows the presence of pure silver chloride. Furthermore, it's important to show that the presence of some silver trace, in this case 1 millimolar of silver, doesn't produce any interference in terms of peak intensity, but just a shift of peak potential towards more anodic potential. Finally, nitrate ions were detected in rainwater without any sample pretreatment. Using the standard addition method, a concentration of 17 micromolar were detected. A river water sample was collected from Oreto River in Palermo and tested without any pretreatment. By the way, the analysis didn't produce any peak due to the presence of chloride ions. So after the addition of silver sulfate, a peak of nitrate appears, and using again the standard addition method, a concentration of 22 micromolar of nitrate were detected. This is an important result because it confirms the chloride removal and shows the applicability of the proposed sensor. Finally, a commercial drinking water was tested without the addition of silver sulfate, and 4.45 ppm of nitrate were detected. This value perfectly matches with the concentration in the datasheet of the water, showing again the applicability of the proposed sensor. So, concluding, in this work, a nanostructured copper-based electrode has been synthesized for the detection of nitrate ions in water samples. Copper nanowires electrodes deposition was optimized in order to increase the electrode sensitivity, and the nanowires were successfully fabricated by the simple galvanic process. The electrode synthesis is cheap, highly reproducible, and the detection procedure is simple and rapid. The nanowires electrode can detect nitrate ions with high sensitivity and low limit of detection, and the limit of detection is almost 1,000 times lower than the maximum allowed concentration imposed by the Environmental Protection Agency. The proposed electrode can quantify nitrate ions even in high chlorinated samples by previous addition of silver sulfate. So here I conclude. I thank you for your attention, and if you have any question, please don't hesitate to ask. Thank you.